What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we're following up to our Going Mobile lab and talking about the definition of torque in a mathematics sense. So we kind of discussed what torque is in a verbal sense. It is an outside force that acts at a pivot point on an object, a fixed pivot point, that causes changes in angular motion. And if you don't quite understand that yet, go back and watch a previous video where I explain the basics of torque. That's more of my verbal explanation of torque and what it is in terms of words. Today, we're going to look more specifically at what that means mathematically and how we can use that verbal definition to construct a mathematic definition, and then use our mathematic definition to go ahead and analyze some torque problems that aren't just simple level balancing problems like our Going Mobile lab. So, if we think about the Going Mobile lab, a lot of us had some amount of error, okay? Meaning that our beams were not level when we first hung them. Here was the hook, here was the pivot point. If I hung them from the center of a hook, they weren't level to begin with. Now, they were stationary. They were definitely balanced, right? The net torque was 0, but they were not level. And the reason that matters is because if I think about where the force of gravity is, if the beam is going to tilt a little bit this way, that means the center of mass is not directly in the center of the object. It's offset to one side, and it's going to be offset to the side that sags down a little bit. That means Fg for this board, if a board hangs like this, not perfectly level when it's hung from the middle, Fg is going to be here. And what I notice about this is that Fg is not making a perpendicular force to the board. So Fg is not the force that is balanced out on both sides of this beam, but some component of Fg is. We know from our definition that a torque is a force acting at a pivot away from a pivot on an object that causes rotation. But we also know that there are certain forces that won't cause rotation. For example, any force that acts at a pivot point will not cause rotation. Any force that acts exactly inward or outward from the pivot point won't cause angular changes. So there is some amount of component force to this. There's some amount of thing. And so what we've seen before is an equation written like this. We saw earlier that torque is equal to F perpendicular times R. And essentially what that statement says is that forces are going to only cause torques if they are acting in some perpendicular component to the board or to the beam or to the seesaw or what have you. So I need to find a way to mathematically describe this. And our perpendicular describing variable is sine theta. It's our function that tells us the perpendicularity of something. Let's look at our equation sheet. Our equation sheet for AP Physics 1 says this. It says that torque, which is a vector, is equal to FR sine of theta. Let's break down what those variables mean. I know what a force is. This is a push or a pull. And I know what R is. R is a distance measurement that is reserved for objects that rotate, like circles, for radius. It has a measurement to a certain middle point. So this here is a distance value from a pivot to a force. What do you know, folks? Force and radius, F and R, those two variables, the first two variables are related. They're not arbitrary numbers pulled out of thin air, plucked off a picture, and plugged into a calculator. They are related. It's not just force times distance. It's force times the distance that force is acting at from our pivot point. These two variables are so closely related. And then there's a third function inside this equation. We have sine of theta. And sine of theta is also related to the previous two variables. Again, this is a vector, and so far, distance isn't really a vector quantity. And it's hard to say F is a vector quantity in this case because, it acts up and down, left and right. I need some other direction component because this is rotating. So up, down, left, right for a force doesn't help me figure out rotation. So I need some other component to help me figure out the rotation. Which way is this thing going to rotate, and which part of the force is going to rotate the beam? This sine theta is the angle between my previous two variables, the force vector and R, or the lever. It's the measurement between the two. So if I go back to my weird hook stick that wasn't level but was balanced, here's the hook, there's the axis of rotation, here is FG. This angle between the beam or the lever, these angles here, it's these angles between the lever and the force. This angle here is sine theta. And we like to keep the angle below 90 degrees, so we go for the smaller angle. That angle there, that angle right there, this itty bitty angle over there, that's the sine theta we are talking about. So this equation here helps us figure out mathematically what a torque value is based on a push or pull that acts at a distance from a pivot point and incorporates the angle at which that force is pushing or pulling relative to that lever or length. Think about it like this. If a force is perpendicular, sine of 90 is 1. Okay, if a force is perpendicular to a beam, it's going to cause rotation. If a force is parallel to the beam, pushing in on the side, pulling away on the side, if it's parallel, sine of 0 degrees is 0. If it's sine of 0, parallel to the beam, it won't cause a torque. If it's perpendicular, it will cause a torque. Anywhere in between, it will cause a torque of less than we would expect, right? Of less than it would if it was perpendicular. Let's give an example. As an example, I've got a board. Here's the board. It's shaded in right here. This is my board, and then there's a string attached to that board, and it's holding that board up. Call it a drawbridge if you want, if you're a big Castle Game of Thrones fan. It's a drawbridge, basically, okay? There's a hinge down here where this thing will rotate around if that string were to snap, and I've got some forces. This force here is Fg. This force here, this string, has a tension force, and that string is acting all the way at the edge. If I think about these things, I've got some angles. The angle up here is 30 degrees. I'm calling that 30 degrees, okay? That makes the angle down here 60 degrees, and you can go ahead and do some math on that if you have to. Where were we? We were talking about this. Let's do this again. I've labeled my picture. It's 30 degrees from the tension to the board. And if I think about that, that also makes this angle down here 60 degrees between the vertical and the board, which means this angle here between these two forces, between that force of gravity and the board is 60. So I've labeled my forces, right? I've got 30 up here at the tension force. I've got 60 between the board and Fg. Both of these I'm keeping less than 90 between the board and the force being applied. Okay? I've got my length of the board is 2 meters. The mass of the board is 3 kilograms. And so if I look at this picture, it looks done. Everything I can think of that's obvious to me is there. But I'm actually missing 2 forces. Let me show you how I know that. I know that because if I go ahead and write my F net, which should be 0 newtons, this system shouldn't be accelerating in any direction. If I write my F net in the, say, X direction, the only force I have is tension. And if that were true, then the tension would be actually accelerating my beam across this page or across this system, and that doesn't make any sense. The board is not moving, the drawbridge is not moving, so there must be a second force. And there is. There is a normal force acting at the hinge, or at the wall, and we call it a hinge force. F hinge in the X direction. This is a force that supports this drawbridge from moving across the page to the left. Similarly, in the Y direction, again, not accelerating up or down, we know that there's the weight of the board, but there also needs to be something supporting the weight of the board, acting against it, holding it up. At the hinge, where the drawbridge meets the wall, we have another hinge force. Hinge in the Y direction. Now, These are two hinge components. Technically speaking, that board acts at an angle. This hinge force is probably right up the board. The force is probably pushing right up, but that's not as useful for me. No matter what, I'm going to have to break it into components to fit it into an F net X, F net Y. So I just break them into components to begin with. There's going to be a hinge force in the X and Y direction always to balance out these forces and hold it in what we call static equilibrium. So this is there for the forces. This is a complete FBD. Both of the hinge forces, however, are acting at the axis of rotation or the pivot point. And because of that, they're not going to cause any rotation. They will simply hold the board in static equilibrium in terms of forces. They're not going to play a role in the torque of this system. Let's see what forces do play a torque in this system by writing our net torque. It's not rotating or changing its rotational motion, so net torque is equal to 0. I've got the tension force acting counterclockwise, so torque from Ft is acting counterclockwise. Fg is acting clockwise, so torque of Fg is clockwise. Here is my net torque expression. Let's go ahead and find that tension force. We don't know it. Let's find it. 0 newtons, Newton meters, is equal to Ft times R for the tension force times sine of theta for the tension force minus mg, because it's Fg, and by this point in the year, we've got to know Fg is always mg, weight of the board, times the radius or distance to that force times sine theta for Fg. I can start plugging in some numbers. Let's do that. I'm going to grab my chair. I've got 0 Newton meters is equal to Ft, that's what I'm solving for, times the distance to Ft. How long is the board? The board is 2 meters. Times sine of the angle between the drawbridge or board and the string, that's 30 degrees. Make sure your calculator's in degree mode. Minus the torque from the weight of the board. We got mg, that's 3 kilograms, times baby g, times the distance between the pivot and the center of mass, 1.5 meters, times sine of the angle between Fg and the board. It's got to be 60. Make sure your calculator is in degree mode, not radian mode. Based on your math class, you may have different modes for your calculator that you're in. In this class, I got to be in degree mode. Physics 1, we're always in degree mode. I do my algebra, my fancy algebra. I don't forget to throw in G and make sure my signs match up. I end up with the tension force being equal to something like 25.5, 26, somewhere in there, based on how you round. It's somewhere between 25 and 26. This is what I end up with. Now, I found the tension force, this unknown tension force. A follow-up question to this, and a common follow-up question to this is, what are the values of the hinge forces then? If I know what tension force is, what are the values of the hinge force? But we've done that before, so I'm going to leave that for you to do on your own. On your own, if you can do all of this and find the tension in the string using torque and angles, using the definition of torque mathematically, you should definitely be able to find the hinge force values. Okay? I'll drop it in the comments so you can check your answer down there. Otherwise, if you have questions, you drop it in the comments if you can. Send me an email if you need to, or ask me in class. Until next time, see ya!